If the idea that our best planetary defense telescope might not be ready the next time the swarm comes around has you wanting to stay on this story, make sure you hit like and subscribe to Signal Watch so you don't miss a single update as this investigation unfolds. Drop a comment below with where you're tuning in from, what time it is there, and this. What should we do with the 6 years between now and 2032? Should we be pointing every available telescope at the Taurid swarm the moment it's visible, or is there something more urgent? Share this one on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Now, a debris field so massive it occupies a significant fraction of Earth's orbital path, and a dense core within it that has never been directly observed despite nearly 30 years of searching. The detection blind spot that made Tunguska impossible to predict in 1908, and that makes the most dangerous part of the next encounter equally invisible to every ground telescope operating today. A dedicated survey telescope specifically designed to close this blind spot, whose launch keeps getting pushed back at the worst possible moment in the history of this threat. And the paper, published at an International Planetary Defense Conference in October 2025, that named two specific years, 2032 and 2036, as the windows when everything either comes into focus or doesn't. Now settle in and let's get into it. The morning of June 30th, 1908 began quietly across the remote Siberian taiga near the Podkamennaya Tunguska River. The region was thinly populated, a scattering of Evenki reindeer herders, a handful of Russian trading posts, hundreds of miles of boreal forest in every direction. It was approximately 7:14 in the morning, local time, when everything changed. Witnesses along a corridor nearly 1,000 kilometers long reported the same sequence. First, a light brighter than the sun, a blue-white fireball crossing the sky from the east-southeast, visible in broad daylight. Then a column of fire rising from the horizon. Then the sound, which took minutes to arrive. Not a single explosion, but a series of concussive blasts that people described as artillery fire, as thunder directly overhead, as the sky being torn. The ground shook. Buildings lost their windows. Horses were knocked from their feet. One witness, S.B. Semenov, was sitting on the porch of a trading post more than 60 kilometers from the epicenter when the heat wave hit him with enough force that he felt his shirt might catch fire. The shock wave that followed knocked him off his chair. Nobody died in the populated areas because there were almost no populated areas. The object detonated above one of the most remote places on the surface of the Earth. And that single fact, that it hit the taiga rather than a city, is the reason you've never heard this story framed as the catastrophe it actually was. Because catastrophe is the right word. The object exploded at an altitude of between 5 and 10 kilometers above the Siberian forest. It never hit the ground. There is no crater. What it left instead was a pattern of destruction that Leonid Kulik, the Russian mineralogist who led the first scientific expedition to the site not until 1927, 19 years after the event, described as something no language seemed adequate to capture. 80 million trees, flattened, 2,150 square kilometers of boreal forest, laid out in a radial pattern pointing away from a central zone where the trees still stood, stripped of every branch, like telephone poles driven into the soil, because the blast had come from directly above them. The energy released was somewhere between 10 and 15 megatons of TNT. Some estimates reach 30. Even at the conservative end, that's 1,000 times the atomic bomb dropped on Hiroshima. One explosion, no crater, no warning. Nobody saw it coming, and this is where the investigation begins. Not with what it destroyed, with what nobody noticed at the time, where it came from. The object approached from the east-southeast, at an entry angle consistent with a shallow trajectory from the direction of the rising sun. It was traveling at approximately 27 kilometers per second, roughly 100,000 kilometers per hour. It was somewhere between 50 and 60 meters in diameter when it entered the atmosphere. By the time it mattered, it had already done what it came to do. Nobody predicted it. Nobody detected it in advance. No scientific institution issued a warning, because in 1908, No such institution existed, and no such capability was even theoretically available. The sky was simply empty, and then it wasn't. That's the story as most people understand it, a freak event, an unlucky intersection of a stray rock and a planet, the kind of thing that happens once every few centuries and then doesn't happen again for a while. A natural disaster, tragic in the abstract, survivable because of geography, best filed under extraordinary but not systemic. The problem with that framing is the word stray, because the Tunguska object wasn't a stray rock. It came from somewhere specific. It belonged to something, and that something, the system of debris it was part of, the orbital structure it inhabited, the stream it traveled in, is still out there, still crossing Earth's path, still producing objects large enough to do exactly what happened in Siberia, and still approaching from the one direction where no telescope on the planet can see them. We're going to tell you what that system is, why it's structured the way it is, and why the people who study it for a living gathered at an international Planetary Defense Conference in Cape Town, South Africa, in October 2025, and formally stated that two specific years, 2032 and 2036, represent elevated risk windows that require targeted surveys, and why the instrument they're counting on to conduct those surveys has been delayed, defunded, and pushed back so many times that its presence in orbit when those windows open is genuinely uncertain. But to understand any of that, you first need to understand the inheritance, the dead giant that left this mess behind. In the night sky of October and November, on clear evenings in the northern hemisphere, you can sometimes see them, slow-moving meteors radiating from the direction of the constellation Taurus, fireballs, occasionally, bright enough to cast shadows, sometimes trailing visible smoke, the Taurid meteor shower. Most years, they're unremarkable, producing fewer than 5 meteors per hour at peak. Skywatchers prefer the Perseids, the Leonids, the faster and more prolific showers that dominate the headlines. The Taurids tend to get overlooked, which is, in retrospect, exactly the problem. The Taurids are not a small meteor shower. They are one of the largest meteoroid complexes in the inner solar system. The stream that produces them is vast, so spread out in space that Earth takes several weeks to pass through it compared to the brief peaks of other showers. The particles in it are heavier than most meteor shower material, pebbles rather than dust grains. And unlike most meteor showers, whose parent bodies have been identified and proved modest, the Taurid stream's origin story is something else entirely. The leading scientific hypothesis, first published in 1984 by two astronomers at Oxford and Armagh Observatory, proposes that the Taurid stream is the debris field of a dead giant, a comet approximately 100 kilometers in diameter. To put that in physical terms, the comet that killed the dinosaurs 66 million years ago was roughly 10 to 12 kilometers across. The Taurid progenitor in this hypothesis was 10 times that size. Not a typical comet, a behemoth comparable to the large objects that populate the Kuiper belt beyond Neptune. Victor Klube of Oxford University and William Napier of Armagh Observatory published their hypothesis in the monthly notices of the Royal Astronomical Society, Volume 211, in 1984. Their argument, assembled from orbital dynamics, the unusual structure of the meteor stream, and the anomalous density of large particles within it, was this: somewhere between 10 and 20,000 years ago, this giant comet entered the inner solar system and fragmented. Catastrophically, the breakup produced a complex of dust, meteor streams, and relatively large bodies that are still present today. And the Taurid meteor shower, both the nighttime October and November streams, and the daytime June and July streams, is what's left of that event. The most obvious surviving piece of the original comet is an object called 2P/Encke. It's an unusual comet by any measure. It has among the shortest orbital periods of any known comet, completing one full loop around the Sun every 3.3 years. Short-period comets are typically thought to have had their orbits altered by gravitational interactions with the giant planets, drawn from the outer solar system inward. 2P/Enki is believed to be a large remnant of the original fragmented giant, now stripped of most of its original volatile material by millions of years of solar heating, orbiting in this truncated 3.3-year path as a kind of ghost of its former self. Every year, as the Earth crosses the orbit of 2P/Enki and its associated debris trail, we pass through the Taurid stream. Twice. The first crossing, in October and November, produces the familiar nighttime Taurid showers. The radiant, the point in the sky that the meteors appear to originate from, lies in the constellation Taurus, high in the night sky in the hours around midnight. Observers can watch. Film crews set up cameras. Fireball networks record the brightest events. The second crossing is different. In June and July, Earth passes through the stream again, through what astronomers call the Beta Taurid shower. But the June encounter approaches from the other side, from the direction of the sun. The radiant of the Beta Taurid shower lies only 10 to 15 degrees west of the sun on the peak dates of June 28th and 29th. You cannot see it. The sky is too bright by orders of magnitude. The Beta Taurids exist as a radio and radar phenomenon, detectable by bouncing radio waves off the ionized trails they leave, but essentially invisible to optical astronomy. They happen in broad daylight, and most years they pass without anyone noticing. Klube and Napier concluded something that almost nobody in 1984 wanted to take seriously, that the Tunguska event of June 30th, 1908, was almost certainly caused by a member of this group, not a random asteroid, not a stray comet nucleus, a fragment of the Taurid complex, a chunk of the original dead giant, still traveling the same path, intersecting Earth's orbit in June, approaching from the direction of the sun, invisible right up until it hit the atmosphere. The date was too specific to ignore. The trajectory was too consistent with the Beta Taurid radiant to dismiss. The orbital mechanics matched. Tunguska was a Beta Taurid event, and if Klube and Napier were right about the progenitor, then what hit Siberia in 1908 was not a statistical outlier. It was a sample from a population that still exists, a population that still crosses Earth's orbit twice a year. The question, the one that would take another decade to begin answering properly, was whether that population contained more objects like it, whether the inheritance of the dead giant included other city killers, whether the stream carried something denser, something more concentrated, something that had been held in place by a mechanism Klube and Napier hadn't yet fully described. It would take David Asher at Armagh Observatory, working with the orbital mathematics in detail, to find what was hiding inside the stream. The Taurid meteor stream, spread out across a wide arc of the inner solar system, is in some ways what you'd expect from a cometary breakup, a diffuse distribution of material, spread by orbital evolution over thousands of years, producing modest meteor rates and occasional fireballs when Earth passes through the denser regions. That's the broad stream, and on its own, it's not alarming. But David Asher noticed something that the broad picture was obscuring. In 1993, working at Armagh Observatory, Asher published a paper with Victor Klube in the Quarterly Journal of the Royal Astronomical Society, Volume 34, pages 481 through 511, that described a specific structure within the Taurid stream, a concentration, a cluster of debris that wasn't randomly distributed across the orbital path, but was instead being actively organized by gravity into a coherent, persistent structure. Asher called it the Taurid Resonant Swarm. The mechanism organizing it is a 7-to-2 mean motion resonance with Jupiter. What that means in plain terms is this: objects trapped in this resonance complete exactly 7 orbits of the Sun for every 2 orbits that Jupiter completes. The orbital period works out to roughly 3.3 years, the same as 2P/Enki. This is not a coincidence. Jupiter, the most gravitationally powerful body in the solar system after the Sun, acts as a shepherd. It repeatedly encounters the same part of the debris stream at the same points in its orbit, and over thousands of years, this gravitational shepherding has concentrated material into a tighter cluster rather than allowing it to disperse uniformly around the orbital path. The implication is not abstract. The broader Taurid stream is relatively thin, spread across enough orbital space that Earth's passage through it is unremarkable in most years. The swarm is different. It's a denser concentration of material, and crucially, Asher's model predicted that this swarm would approach Earth not every year, but in specific years, when the orbital geometry placed the swarm's position near the point where Earth's orbit and the Taurid path intersect. Those years would produce elevated fireball rates, larger than normal Taurid meteors, and potentially encounters with objects in the meter to 100-meter size range that the normal annual showers don't produce. The model made specific testable predictions, and the predictions came true. In 1998, Taurid fireball rates elevated above background. In 2005, observers around the world reported unusual fireball activity in late October and early November, what skywatchers started calling the Halloween fireballs. In 2015, the most well-documented encounter to date, the South Taurid shower produced rates of 10 meteors per hour with numerous fireballs, many of them bright enough to light up the landscape. The European Meteor Network, a distributed array of all-sky cameras across the continent, recorded more than 100 bright Taurid fireballs during that 2-week window. Astronomers Pavel Spurny and Jiří Borovička at the Czech Academy of Sciences analyzed the fireball data and published their results in Astronomy and Astrophysics in 2017. The fireballs were strongly associated with the 7-2 mean motion resonance with Jupiter. That phrase is important. It wasn't just that there were more fireballs. It was that the orbits of the objects producing those fireballs were tightly clustered in exactly the range of orbital parameters the swarm model predicted. This was, as Spurny and colleagues concluded, among the strongest quantitative dynamical evidence to date for the Taurid Resonant Swarm. During the 2015 encounter, 2 Taurid-associated asteroids with very similar orbits were found by Arkadiusz Olech and colleagues at the Polish Academy of Sciences, objects that appeared during the exact window the swarm model predicted. Their statistical significance was unclear, but their orbital similarity to the fireball-producing material was striking. In 2022, the swarm returned. Fireball sightings increased again worldwide. Observers reported multiple bright events per night during the first 2 weeks of November. In 1975, during a swarm passage, something was recorded that doesn't get much attention: the Apollo seismic network. The lunar seismometers left on the moon's surface by the Apollo astronauts detected elevated impact signatures. The swarm didn't just graze Earth, it hit the moon. So the swarm is real, in the sense that its predicted signatures, elevated fireball rates, concentrated orbital clustering, lunar seismic anomalies, have now been confirmed across multiple encounters spanning nearly 3 decades of observation. The question that David Asher's model raised in 1993, and that nobody has yet been able to definitively answer, is what's in the swarm at the sizes that matter most. The fireballs confirmed are meteors, centimeter-to-meter class objects, spectacular but not dangerous. What the swarm might also contain, what the physics of the original cometary breakup suggests could exist within the resonant zone, is objects at 50 meters, 100 meters, several hundred meters. Objects like the one that hit Siberia in 1908. The swarm visits Earth on a roughly 3 to 7 year cycle, driven by Jupiter conjunction geometry. The previous encounters, 2005, 2015, 2022, have all been studied with increasing sophistication. What every study has established is fireball enhancement. What no study has been able to establish or to rule out is a population of large, dark, city-killer class objects traveling silently alongside the fireballs, undetected in the same resonant zone. In 2019, a team of 3 astronomers at the University of Western Ontario decided that needed to change. They ran the numbers, identified the best observing window in more than 4 decades, designed a specific survey using a specific telescope, and published their proposal. What happened next is one of the more extraordinary failures in the history of planetary defense research. And it starts not with a budget cut or an equipment failure, but with a protest on a Hawaiian mountain. David Clark, Paul Wiegert, and Peter Brown work in the Department of Physics and Astronomy at the University of Western Ontario. In 2019, they published a paper in Monthly Notices of the Royal Astronomical Society Letters, Volume 4, 87, pages L35 through L39, that set out to quantify something nobody had quantified before: how dangerous a search of the Taurid Resonant Swarm was actually warranted. To do this, they built a simulation. 10,000 synthetic Taurid asteroids, each 100 meters in diameter, with orbital parameters drawn from the high-precision fireball data of the 2015 encounter. They forced all 10,000 objects into the 7-2 mean motion resonance zone. Then they computed their positions forward 1,000 years, identifying every moment when one of those hypothetical objects would pass close enough to Earth to be observable or close enough to be dangerous. The purpose of the simulation was not to predict an impact. It was to establish what the observing windows looked like, when the geometry would allow a ground-based telescope to actually see into the swarm and detect something if it was there. The answer pointed to a specific window, June and July of 2019. Earth was scheduled to pass within 0.06 astronomical units of the swarm center. That's roughly 9 million kilometers, in its closest post-perihelion approach since 1975. For anyone trying to search for large objects in the resonance zone, this was not a good opportunity. It was the opportunity. Clark, Wiegert, and Brown proposed using the Canada-France-Hawaii telescope on Mauna Kea to conduct a dedicated survey during this window. The CFHT is a 4-meter class optical telescope with a wide-field imaging camera capable of detecting objects in the 100-meter size range at the distances relevant to the swarm approach. The team had a target, a method, a telescope, and a window. Before we talk about what happened to that window, it's worth pausing on the math of what they were looking for. The Tunguska object, the one that flattened 2,150 square kilometers of Siberian forest with 10 to 15 megatons of energy, was somewhere between 50 and 60 meters in diameter. Clark, Wiegert, and Brown were simulating objects at 100 meters. That size difference matters more than it sounds. Kinetic energy scales with the mass of an object, and mass scales with the cube of diameter. A 100-meter asteroid of the same density and velocity as the Tunguska object carries roughly 8 times the kinetic energy. Tunguska produced the equivalent of 1,000 Hiroshimas. A 100-meter object of similar composition would produce the equivalent of roughly 8,000 Hiroshimas, somewhere in the range of 100 to 300 megatons, depending on composition, entry angle, and whether it reaches the ground or explodes in the atmosphere. This is the size class that NASA's NEO Surveyor mission was mandated by Congress to catalog. Objects 140 meters and larger, capable of devastating a region the size of a major country. Objects 100 meters and smaller still qualify as what planetary defense researchers call city killers, large enough to obliterate a metropolitan area if they strike in the wrong place. As of the Clark, Wiegert, and Brown paper, the total number of confirmed Taurid Resonant Swarm members in the hazardous size range, anything from 100 meters upward, was 0. Not 0 confirmed threats, 0 confirmed members at any level. The swarm, as an object class, had never been directly observed at the sizes that would matter for an impact event. Every piece of evidence for its existence came from the fireball and seismic data, from the small end. The large end remained completely unknown. The 2019 survey was designed to change that. To look directly into the swarm's core at the closest geometry in nearly half a century, and either find the large objects finally putting observational constraints on the hazardous population, or establish firm upper limits on how many there could be. There was a congressional mandate supporting this work. Incidentally, the George E. Brown Jr. Near-Earth Object Survey Act, passed in 2005, directed NASA to catalog 90% of near-Earth objects larger than 140 meters. That mandate was not new in 2019. It had been on the books for 14 years. The mission being planned to fulfill it, the infrared space telescope that would eventually be named NEO Surveyor, was still years from launch. In the meantime, the 2019 Taurid Swarm window was the best available opportunity to characterize the most concerning known debris structure in Earth's orbital neighborhood. The telescope was available, the proposal was published. The geometry was better than it had been in 44 years. And then Mauna Kea happened. In the summer of 2019, a controversy that had been building for years on the island of Hawaii came to a head. The planned construction of the 30-meter telescope, a next-generation observatory that would have been the most powerful optical telescope on Earth, had long been contested by native Hawaiian groups who considered Mauna Kea, the volcano where the telescope was to be built, sacred ground. In July 2019, as the project reached its construction phase, protesters physically blocked access to the summit road, shutting down operations at multiple observatories on the mountain, including the Canada-France-Hawaii telescope. The timing was, from a purely astronomical standpoint, catastrophic. The observing window Clark, Wiegert, and Brown had identified for their Taurid Swarm survey ran from roughly July 5th through August 10th, 2019. The CFHT was their instrument. The mountain was closed. This is confirmed explicitly in the 2025 paper by Paul Wiegert and colleagues, published on Archive in June 2025. A 2019 opportunity went untapped when protests at Mauna Kea prevented telescope operations at the CFHT during the observing window. One sentence. Decades of preparation, the most favorable geometry in 44 years, and one sentence. The significance of this failure is hard to overstate, but it requires some care in framing. The protests on Mauna Kea were not conducted by people who knew they were preventing a planetary defense survey. The telescope mount dispute is a genuine, long-standing conflict over indigenous sovereignty and the use of sacred land, with legitimate interests on all sides. The astronomical tragedy is not anyone's fault in a simple sense. It is simply what happened. The geometry aligned, the telescope was unavailable, and the window closed. The swarm passed at its closest approach to Earth since 1975 without a single dedicated observation of its potentially hazardous population. The next swarm encounter with favorable geometry came in 2022. The scientific community was ready this time, deploying two separate instruments, the Canada-France-Hawaii Telescope's Megacam Imager over 3 nights from October 29th through October 31st, and the Zwicky Transient Facility, a wide-field sky survey at Palomar Observatory in California. The 2022 campaign was genuinely productive, not in the sense of finding swarm members, but in establishing what the data says their absence means. The Zwicky Transient Facility results, analyzed by Jasmine Lee and colleagues, and published in the Planetary Science Journal in 2025, found no positive detections in the hazardous size range and provided an upper bound. Fewer than 9 to 14 objects brighter than absolute magnitude H equals 24 in the survey footprint. The CFHT Megacam results, published by Wiegert, Vida, Clark, and Eagle in June 2025, ArcSIF paper 2506.03327, were more comprehensive. Observations reaching magnitude 24.5 in the combined grief filter over 3 nights, more than 1,000 moving objects detected and assessed. 8 candidates showed on-sky motion rates consistent with Taurid orbital parameters. 7 were subsequently identified as unrelated objects, Hungarias, Mars crossers, background asteroids that happened to be moving at similar apparent rates. One object, approximately 60 meters in diameter, had motion consistent with a Taurid swarm member, but insufficient orbital data to confirm it. Its orbit remains ambiguous. The combined result, consistent with no confirmed Taurid Resonant Swarm members at the potentially hazardous size range. And an upper bound that sounds reassuring until you read the fine print. The upper bound from the Megacam survey is fewer than 3,000 to 30,000 objects brighter than absolute magnitude H equals 25.6 plus or minus 0.3. In physical terms, that corresponds to objects somewhere between 34 and 78 meters in diameter, assuming a reflectivity similar to Comet 2P/Encke. 95% confidence level. This means the surveys are technically consistent with the swarm, containing up to 30,000 objects in the 34 to 78 meter size range without having detected any of them. That upper bound is not a prediction. It's a limit on what can be excluded, and crucially, the surveys targeted the smaller end of the hazardous range. They do not effectively constrain the population at 100 meters and above, the size that starts matching the Tunguska impactor, because the surveys weren't deep enough or wide enough to confidently exclude large objects at those sizes. The total count of confirmed Taurid Resonant Swarm members in the city killer size range after the best available surveys across 2015, 2019, and 2022, 0. That result is not reassuring. It is unresolved. Because we haven't found them is not the same as they're not there. And the reason that distinction matters is not abstract. It connects directly to the one structural feature of this entire story that makes everything else more difficult. The Taurid swarm doesn't only visit in October and November, when it's visible at night and telescopes can observe it freely. It also visits in June and July. And in June and July, it comes from the direction of the sun. On the morning of February 15th, 2013, a meteor the size of a semi-trailer entered Earth's atmosphere over the Ural Mountains in Russia. It was just after sunrise. The sky was clear and bright. Nobody saw it coming. The object was approximately 20 meters in diameter. It weighed roughly 13,000 tons. It entered the atmosphere at a speed of more than 40,000 kilometers per hour and exploded at an altitude of approximately 30 kilometers above the city of Chelyabinsk. The blast released approximately half a megaton of energy, the equivalent of 35 Hiroshima bombs. The shockwave shattered windows in more than 7,000 buildings across 6 cities. More than 1,500 people were injured, most of them by flying glass. 20,000 square meters of glass were blown out across the region. The physical damage was estimated in the hundreds of millions of dollars. It was the largest asteroid strike on Earth in more than a century, and no observatory on Earth saw it coming. Not one. The entire global network of telescopes, tracking stations, survey cameras, and planetary defense infrastructure that humanity had built by 2013 failed completely to provide a single second of advance warning. Richard Moisel, the head of planetary defense at the European Space Agency, has stated plainly, asteroids the size of the Chelyabinsk meteor strike Earth roughly every 50 to 100 years. Once every 50 to 100 years. In other words, an object this size hits with zero warning, not because our instruments are poorly calibrated, not because our software is outdated, because of where it came from. Chelyabinsk approached from the direction of the rising sun. This is not an unusual direction for hazardous objects to approach from. It is, in fact, one of the most common approach geometries for near-Earth asteroids, for a reason rooted in orbital mechanics. There is an entire class of near-Earth asteroids, called A10 asteroids, whose orbits lie almost entirely interior to Earth's. They cross Earth's path at the outermost edge of their orbit, approaching from the sunward direction. Scott Shepard, a staff scientist at the Carnegie Institution for Science, who has dedicated much of his career to finding these objects, has stated A10 asteroids are the most dangerous because they cross Earth's orbit just barely at their most distant point. They spend most of their time between Earth and the Sun, which means they can only be observed when they are at the one point in their orbit where they cross outward. And from Earth's perspective, that crossing happens in the direction of solar glare. Ground-based optical telescopes cannot observe within approximately 30 degrees of the Sun. The contrast ratio is simply too extreme. The sky background, when close to the Sun, is millions of times brighter than a dark asteroid reflecting sunlight, and dark asteroids are common. Amy Mainzer at the University of Arizona, who leads the NEO Surveyor mission, has noted that roughly a third of near-Earth asteroids are as dark as printer toner. These objects are essentially invisible to ground-based optical surveys, even in perfect nighttime conditions. In the direction of the Sun, during daylight hours, they don't exist as far as any telescope on the ground is concerned. The Beta Taurid shower, the June encounter with the Taurid stream, has its radiant located at right ascension 5 hours 18 minutes, declination plus 21.2 degrees. On the peak date of June 28th to 29th, that point in the sky is only 10 to 15 degrees west of the sun. Not a challenging observing angle, not a difficult but manageable constraint. It is the dead zone. No optical telescope on Earth can look there. This is why Tunguska came without warning in 1908. The object entered from the east-southeast on the morning of June 30th, traveling along a trajectory consistent with beta Taurid orbital geometry. Astronomers Duncan Steele, who founded the Space Guard Foundation that advocates for planetary defense, and William Napier of Armagh Observatory, have explicitly named the beta Taurids as the probable source of the Tunguska impactor. It came from where the beta Taurids come from, at the time of year when the beta Taurids are active, along the approach vector that beta Taurid objects follow. In 1908, the lack of warning was expected. No one had the technology to detect a 60-meter asteroid on a collision course. The observation was impossible with instruments that existed. In 2013, Chelyabinsk arrived with the same zero warning, not because the technology had failed to advance, but because the dayside blind spot is structural, an inherent consequence of orbiting a sun that produces more light than any telescope can look through. There is a way to close this blind spot, not from the ground, from space, specifically from a point between Earth and the sun, a position where a telescope could look outward toward approaching objects against the darkness of space rather than against the glare of the solar disk. A position called the Sun-Earth L1 Lagrange point, located approximately 1.5 million kilometers from Earth in the direction of the sun. From there, an infrared telescope, sensitive to the heat signatures of asteroids rather than their reflected light, could detect incoming objects regardless of what direction they're coming from, regardless of whether they're dark or reflective, regardless of the time of day on Earth below. The European Space Agency has a mission to put such a telescope at L1. It's called NEOMIR, Near Earth Object Mission in the Infrared. ESA has described it as the instrument that would close a large blind spot on the dayside hemisphere of Earth and enable us to detect impact hazards similar to the Chelyabinsk event in advance for the first time. It is targeted for launch in the mid-2030s. It will not be operational before the 2032 Taurid Swarm encounter. It will not be operational before the 2036 encounter. NASA has its own mission with overlapping capability. It's been in development, in various forms, since 2006. It keeps getting delayed. Its name is NEO-Surveyor, and the story of what has happened to it between its conception and today is one of the most important stories in this entire investigation, because the question of whether it's operational in orbit by 2032 is not an astronomical question. It's a political one. The idea behind NEO-Surveyor is straightforward. An infrared space telescope positioned at the Sun-Earth L1 Lagrange point, scanning the sky for the heat signatures of asteroids. Because it detects thermal emission rather than reflected sunlight, it can find objects that are dark, the class most likely to be missed by ground-based surveys. Because it's at L1, between Earth and the Sun, it can look in directions that ground telescopes cannot. And because it surveys from space, it operates continuously, uninterrupted by weather, daylight, or the atmospheric blurring that limits ground-based resolution. The mission concept has been called various names over the years. NEOCOM, the Near-Earth Object Surveillance Mission, NEO-Surveyor. The principal investigator throughout has been Amy Mainzer, now a professor at the University of Arizona's Lunar and Planetary Laboratory. The concept was first proposed in 2006, when a study group at JPL began designing a next-generation asteroid-finding infrared telescope to follow up on the early success of the WISE mission. It competed multiple times for NASA Discovery Program funding, a program for lower-cost planetary science missions, and lost multiple times, not because reviewers found it unscientific, but because it was competing for funds against missions unrelated to planetary defense, and planetary defense kept losing. This, despite a 2005 congressional directive, the George E. Brown Jr. Near-Earth Object Survey Act, that had explicitly mandated NASA to catalog 90% of potentially hazardous asteroids larger than 140 meters. The mandate had no associated funding. It was an instruction without a budget line. In July 2019, an asteroid called 2019 OK passed within 73,000 kilometers of Earth, closer than the Moon. It was 250 meters across. It arrived without meaningful advance warning, slipping through the detection network until roughly 24 hours before its closest approach. This event, coming in the same month as the Mauna Kea closure that killed the Taurid survey opportunity, finally broke the political logjam. In September 2019, NASA's Associate Administrator for Science announced that NEOCAM, now renamed the NEO Surveillance Mission, later NEO Surveyor, would be funded outside the competitive discovery process, directly from the Planetary Defense Coordination Office budget. The argument was national security. An object this size striking a populated area would be a civilizational event, not just a natural disaster. The original launch target was the first half of 2026. That date no longer exists. In fiscal year 2023, NASA's budget request for NEO Surveyor was $39.9 million. The project needed roughly $90 million to stay on a 2026 launch timeline. Congress, recognizing the underfunding, directed NASA to spend no less than $90 million on the mission. That helped, but not enough. NASA had already, in June 2022, rescinded $33 million of a prior appropriation and redirected it elsewhere. By August 2022, the project was told to plan on $80 to $90 million in the coming year. Lori Glaze, then NASA's Director of Planetary Science, stated at a meeting of NASA's Small Bodies Assessment Group in January 2023 that the additional congressional funding, while helpful, would not allow NASA to avoid a delay. The launch slipped. The new target became September 2027, with June 2028 as the latest acceptable date. The instrument itself is significant enough to describe in some detail. A 50-centimeter diameter telescope operating in two thermal infrared wavelength channels, NC1, spanning 4 to 5.2 micrometers, and NC2, spanning 6 to 10 micrometers. Both channels detect the heat that asteroids re-emit after being warmed by sunlight. The detector array is 2048 by 2048 pixels, producing 82 gigabits of data per day. The system will be passively cooled to 30 Kelvin, about minus 243 degrees Celsius, without requiring cryogenic fluid, a significant engineering advantage over its predecessor, Neowise, which degraded after its coolant ran out. The nominal mission is a 5-year baseline survey. After launch and a 6-month survey verification period, it would conduct active asteroid surveys and would be specifically capable of detecting objects approaching from the direction of the Sun. Mainzer's own framing of the instrument's dayside capability: by searching for NEOs closer to the direction of the Sun, NEO Surveyor would help astronomers discover impact hazards that could approach Earth from the daytime sky. The congressional mandate to catalog 90% of hazardous NEOs was passed in 2005. NEO Surveyor is currently scheduled to launch no earlier than September 2027, 22 years after the mandate it exists to fulfill. If it launches on time and its 6-month verification goes smoothly, it would begin active surveys in mid-2028. It would have roughly 3.5 years of operational data before the November 2032 Taurid encounter. That assumes it launches on schedule. The FY 2027 budget proposal released by the White House in April 2026 proposes a 23% overall cut to NASA's budget and a 47% cut to the agency's Science Mission Directorate. NEO Surveyor is still technically funded in the current legislative planning documents. The Senate Appropriations Bill includes $300 million for the mission. But the pattern of this program's history is instructive. It has been funded, partially defunded, redirected, delayed, and restructured so many times across multiple administrations that its current schedule should be understood not as a commitment, but as a projection with a long history of slipping. Mark Boslow, the University of New Mexico research professor, whose 2025 paper we'll get to shortly, has been direct about what this means for 2032. If we discover the objects with enough warning time, then we can take measures to reduce or eliminate the risk. If the new infrared telescope is in operation, then we can potentially have much more warning time. If, that word is doing a lot of work. To understand why 2032 matters more than most swarm years, you need to understand what Earth actually passes through during an encounter, and how the physics of the resonance mechanism produces something more structured than a random debris field. Start with the base rate. In a normal year, the Taurid meteor shower produces roughly 5 meteors per hour at peak. Slow moving, sometimes colorful, occasionally bright, nothing alarming. Of those, roughly 1% qualify as fireballs, objects bright enough to outshine Venus or the full moon, visible over a wide geographic area. Encountering a fireball-class Taurid in a normal year means driving through a stretch of highway and seeing a bright streak. Memorable, not dangerous. In a swarm year, that ratio changes. The fireball percentage rises from 1% to as high as 7% of all Taurid meteors. The absolute rate increases. Observers during the 2015 encounter were reporting several fireballs per night, rather than the typical one per 20 hours. What's producing these events is not random. The European Meteor Network's analysis of 2015 confirmed that the fireball-producing objects were tightly clustered in a narrow range of semi-major axes and mean anomalies corresponding to the resonant region. Jupiter's gravitational shepherding has concentrated not just dust, but pebbles, rocks, boulders, and potentially larger objects into the resonant zone. When Earth passes through that zone, rather than through the diffuse surrounding stream, the encounter rate and the average object size both increase. The 1975 encounter added an element that rarely gets discussed. The Apollo Seismic Network, the set of passive seismometers left on the lunar surface by the Apollo astronauts, was still operational in 1975. During the Taurid Swarm passage that year, the network recorded elevated impact signatures, confirmed in subsequent analysis by Jürgen Oberst and Yoshio Nakamura. The swarm hit the moon. The implications are straightforward. If the swarm was generating enough lunar impact events to register seismically across the Apollo network, the objects producing those impacts were not small. Seismically detectable lunar impacts require impactors in at least the meter class, more likely several meters to tens of meters. These are not the dust-grained Taurids of a normal year. Now consider the November 2032 encounter in this context. The orbital models, including the swarm year table, maintained by David Asher at our Moz Research Archive, show the 2032 encounter as exceptional. Earth will pass very close to the swarm center, the densest region of the resonant cluster. The moon will be new, optimal conditions for observation, no lunar glare washing out the fainter fireballs. The encounter geometry is more direct than any since at least the early 1970s. And this is where the story takes a turn that most people following this topic haven't heard about. Because in October 2025, a paper appeared at the Planetary Defense Conference in Cape Town, South Africa, that quietly changed how researchers are framing the risk from the 2032 encounter. Not by predicting an impact, not by identifying a specific threatening object, but by doing something more subtle and more significant, by showing that the standard way planetary defense calculates impact risk may be systematically wrong when it comes to the Taurid stream specifically. The paper was presented by Mark Boslow of the University of New Mexico, a researcher whose work spans Tunguska modeling, asteroid impact physics, and the debunking of overblown cosmic threat claims, working with Peter Brown, David Clark, and Paul Wiegert at the University of Western Ontario, and Quanji Yi at the University of Maryland. The combination of authors is significant. These are not fringe researchers building a case for something exotic. They are the core of the Western world's Taurid research community, presenting at the primary international venue for planetary defense science, Their central finding was this: standard planetary defense risk assessments are based on what they call stochastic risk, the assumption that near-Earth objects are randomly distributed in orbital space, and that impact probability can be calculated by summing probabilities over the known population, assuming that randomness. This works reasonably well for asteroids distributed across the broad NEO population. It does not work well when a significant fraction of the hazardous population is concentrated in a coherent, non-random cluster that approaches Earth on a predictable periodic schedule. If the Taurid Resonant Swarm contains a substantial number of airburst-class objects in the range of 50 to 200 meters, then their contribution to Earth's impact risk is not randomly distributed across time. It is concentrated in the swarm encounter windows, the November and June passages every 3 to 7 years, and especially the encounters when Earth passes near the swarm's center. The stochastic model spreads that risk evenly across the year and across years. The coherent model concentrates it. The result: the stochastic model may underestimate impact risk during swarm encounter years and overestimate it during non-encounter years. The 2032 encounter on this framing is not just an unusually close pass through a debris field. It's the year when the coherent component of Taurid impact risk, the fraction that the standard model systematically misses, peaks. The researchers were specific about what this means in practice, because there may be a significant or even dominant contribution to the risk from the Taurid Resonant Swarm. Then targeted surveys dedicated to quantification of the population, identification of potentially hazardous objects, and detection of imminent impactors during the passage of the swarm should be implemented. The passive voice of a scientific paper trying to say something urgent without sounding alarmist. The full title of the Boslow, Brown, Clark, Wiegert, and Ye paper is 2032 and 2036 Risk Enhancement from NEOs in the Taurid Stream. Is there a significant coherent component to impact risk? It was published in Acta Astronautica, volume 238, as part of the proceedings of the 2025 International Astronautical Academy Planetary Defense Conference. The conference was held in Cape Town, South Africa, in October 2025. This is worth dwelling on for a moment. The Planetary Defense Conference is not a fringe gathering. It is the premier international forum for the scientific and policy communities working on asteroid impact hazard. Attendees include researchers from NASA, ESA, national space agencies, and universities across the world. Papers published in its proceedings represent the active frontier of what the planetary defense community considers important enough to present to peers. The fact that this paper appeared there, that its authors chose Cape Town as the venue to raise the 2032 question publicly, is itself a signal. The paper's framing is careful and precise, in the way that peer-reviewed science is careful and precise. Boslow does not say the Taurid swarm is going to hit Earth in 2032. He says something more technically nuanced, and, if you follow the implications, more disturbing. The standard framework for thinking about asteroid impact risk is incomplete when applied to a coherent debris cluster, and the incompleteness is not symmetric. It produces an underestimate during swarm encounter years. The reasoning draws on the physics of the resonance mechanism described earlier. In the standard stochastic model, impact risk is calculated as a function of the total known NEO population, with the assumption that objects are randomly distributed in orbital space. The probability of Earth encountering a given object depends on how often their orbits intersect and how large the objects are. This is a reasonable model for a diffuse, uncorrelated population. But the Taurid Resonant Swarm, if it contains a population of hazardous objects, is not a diffuse, uncorrelated population. It's a gravitationally shepherded cluster occupying a narrow range of orbital parameters, periodically cycling close to Earth on a predictable schedule. Hazardous objects within the swarm have correlated orbits. When the swarm is far from Earth, they're all far from Earth. When the swarm is close to Earth, as it will be in November 2032, they're all close to Earth simultaneously. This is what Boslow means by the coherent component. The risk doesn't arrive randomly, a little bit at a time, spread across years. It arrives in concentrated windows. The stochastic model cannot see this structure because it was not designed to see it. It treats all near-Earth objects as if they're drawn from the same uniform population, which they're not. The team incorporated the most recent observational data from the 2022 surveys, the ZTF and CFHT results, and found that these surveys, while constraining the population at the smaller end of the hazardous range, still left the larger end effectively unconstrained. An asteroid 150 meters in diameter, traveling on a Taurid resonant orbit, would have been missed by both the 2022 surveys if it happened to be in the unobserved portion of the swarm volume. The surveys are narrow beams. The swarm is wide. Their recommendation, stated explicitly, is targeted survey campaigns during the 2032 and 2036 swarm node crossings, not passive monitoring, active, dedicated searches during the windows when the swarm is closest to Earth and when observational geometry allows the deepest possible look into the resonant zone. For 2032, ground-based optical surveys during the November encounter window. For 2036, space-based infrared observation during the June encounter, because the June 2036 encounter approaches from the day side, and only an infrared telescope at L1 can look there. Boslow has been direct about the instrument dependency. If we discover the objects with enough warning time, then we can take measures to reduce or eliminate the risk. If the new infrared telescope is in operation, then we can potentially have much more warning time. The words, "if it is in operation," carry the full weight of the NEO surveyor funding history described in the previous section. Boslow knows the timeline. He knows that NEO surveyor is scheduled to launch no earlier than September 2027, and that its operational survey period won't begin until roughly mid-2028 at the earliest. He knows that the June 2036 encounter, the dayside encounter, the one invisible from the ground, the one that comes from the same direction as Tunguska, falls entirely within the window when NEO surveyor should be in its operational phase, assuming nothing else goes wrong. This is important to state clearly. Boslow and his colleagues are not predicting an impact in 2032 or 2036. They are not saying a specific tracked object is on a collision course. They are saying the existing risk framework is insufficient for the swarm encounter geometry. The next major encounter is in 2032. The one after that, in 2036, comes from the dayside, and targeted surveys are needed in both windows. The data to evaluate the actual risk doesn't exist yet. Getting that data requires instruments that are either not yet in orbit or not yet operational. It's also worth noting explicitly what Boslow is not. He is one of the most rigorous critics of overblown asteroid impact claims in the scientific community. He has published a comprehensive refutation of the Younger Dryas impact hypothesis, the contested claim that Taurid complex debris caused a catastrophic cooling event 12,800 years ago. He has helped prompt the retraction of a paper that incorrectly claimed an ancient city in Jordan was destroyed by a Tunguska-scale airburst. He debunks inflated asteroid threats as a matter of professional practice. When someone with that track record publishes a paper saying the risk from the 2032 Taurid encounter may be larger than the standard model suggests, and that targeted surveys are urgently needed, it is not sensationalism. It is the most measured possible version of, we have a problem, and we're running out of time to look at it carefully. 12,800 years ago, the Earth was a different place. The great ice sheets that had covered much of North America and Northern Europe for tens of thousands of years were retreating. Temperatures were rising. Megafauna, mammoths, mastodons, giant ground sloths, short-faced bears still roamed the continents in large numbers. Human populations were present across most of the habitable world, living as hunter-gatherers, beginning, in some places, the earliest experiments with plant cultivation. The archaeological record suggests a world in gradual productive warming transition. And then, approximately 12,800 years ago, something happened. The warming stopped. Temperatures plunged back to near glacial conditions across the northern hemisphere within decades. geologically almost instantaneous. A period called the Younger Dryas had begun, and it would last for roughly 1,200 years. 35 genera of large mammals went extinct in North America. Human cultural traditions that had been stable for thousands of years were disrupted or destroyed. The populations that had been expanding contracted. In 2007, a team led by Richard Firestone at Lawrence Berkeley National Laboratory published a paper in the Proceedings of the National Academy of Sciences, presenting evidence they argued pointed to a cosmic cause. At more than 50 sites across approximately 50 million square kilometers of North America and Northwest Europe, at a geological layer corresponding precisely to the onset of the Younger Dryas 12,800 years ago. They found markers associated with high-energy impact events, nanodiamonds, platinum group element anomalies, high-temperature microspherules, the kind of signatures left by cometary or asteroidal material, exploding at extreme temperatures and pressures. The researchers proposed that the Earth had passed through the debris field of a disintegrating comet, triggering hemisphere-wide airbursts that ignited forests, loaded the atmosphere with impact dust, and initiated the abrupt cooling. The Younger Dryas impact hypothesis generated enormous scientific controversy, and that controversy has not been resolved. Multiple research teams have attempted to replicate the Firestone Group's findings with mixed results. In 2023, a team that included Mark Boslow published a comprehensive refutation in Earth Science Reviews, Volume 247, titled straightforwardly, Comprehensive Refutation of the Younger Dryas Impact Hypothesis. In August 2025, a PLOS-1 paper claiming to have found the impact proxies in Baffin Bay, ocean sediment cores, was retracted after peer review identified significant methodological problems. The mainstream of the planetary science community does not accept the strong form of the hypothesis. What William Napier has contributed, separately from the contested YDIH specifics, is a broader framework for understanding the Taurid complex as a recurring hazard on civilizational timescales. His 2010 paper in Monthly Notices of the Royal Astronomical Society, Volume 412, titled Paleolithic Extinctions and the Taurid Complex, examines the geological and biological record for evidence of episodic bombardment events consistent with the predicted structure of the complex. His argument is not that any specific extinction event was caused by the Taurids. It is that the fragment population produced by the giant comet's disintegration 10 to 20,000 years ago is large enough, and the encounter probabilities over long time frames are high enough that the Taurid complex has almost certainly contributed to impact events on human civilization timescales. The Taurid stream's overall activity cycle peaks roughly every 2,500 to 3,000 years, when the stream's internal structure brings the densest material closer to Earth's orbital path. These are not the 3 to 7 year swarm encounter cycles described earlier. Those are the cycles driven by Jupiter resonance within the swarm. These longer cycles are driven by the broader evolution of the stream itself, as the collective debris cloud slowly precesses around the inner solar system. This is the physical context for 2032, not as an isolated astronomical event, but as one point in a pattern that has been shaping the near-Earth environment since a giant comet broke apart and seeded the inner solar system with its debris somewhere between 10 and 20,000 years ago. The stream is old. The swarm within it is old. The encounter geometry repeats. Klube and Napier have also drawn connections between periods of enhanced Taurid activity and episodes of cultural disruption in the Bronze Age, suggestions that enhanced fireball and airburst events associated with Taurid complex encounters may have contributed to the general crisis of the late Bronze Age collapse around 1200 BCE. This remains deeply speculative and has not achieved scientific consensus. But the physical framework that the Taurid complex represents a debris population large enough to produce episodic airburst events on human timescales is not speculative at all. It follows directly from the orbital dynamics and the fireball statistics. What Tunguska tells us on this reading is not, here's a freak event that won't happen again for 1,000 years. What Tunguska tells us is, Here is a sample drawn from a population. A population that still exists, still crosses our orbital path twice a year, and still contains objects we have never directly observed. I want to address something directly because this topic attracts some claims that deserve an honest answer grounded in physics rather than dismissal. There is a version of the Taurid complex story circulating in certain corners of the internet that is significantly more dramatic than what the evidence supports. It involves hidden government knowledge of imminent impact, suppressed data from astronomical surveys, connections to ancient catastrophes, wiping out advanced civilizations, and a deliberate institutional conspiracy to prevent the public from understanding the true danger. Some of this draws on real scientific hypotheses: the Younger Dryas impact hypothesis, Klube and Napier's coherent catastrophism work, and extends them well beyond what their authors actually argued or what the evidence can support. Let's go through the specific claims. The claim that the Taurid swarm is definitely going to impact Earth in 2032 is wrong. Mark Boslow's paper, the most significant recent scientific statement on 2032 risk, explicitly describes the risk as potentially elevated above background, not as a predicted impact. No specific tracked object in the swarm is on an Earth-intersecting trajectory. The research calls for targeted surveys to characterize the population, not civil emergency response. The claim that the Younger Dryas cooling event, 12,800 years ago, was caused by Taurid complex fragments, and that this proves the stream's catastrophic potential on civilizational timescales. This is actively contested in peer-reviewed science. The same Mark Boslow, who published the 2032 risk assessment paper, also led the comprehensive refutation of the Younger Dryas impact hypothesis, published in Earth Science Reviews in 2023. Vance Holliday at the University of Arizona, who studies the relevant geological record, co-authored that refutation. The PLOS One paper, claiming ocean sediment evidence for the event, was retracted in August 2025 after reviewers identified fundamental methodological problems. The strong form of the YDIH is not accepted by the mainstream planetary science community. The claim that governments are hiding the true danger of the Taurid swarm has a simple problem. Every piece of evidence cited in this episode is publicly available. The Klube and Napier papers are in monthly notices of the Royal Astronomical Society, freely accessible. The Clark, Wiegert, and Brown 2019 paper is in MNRAS letters. The Boslow et al. 2025 paper is in Acta Astronautica and was presented publicly at an international conference. The Wiegert et al. June 2025 survey results are on ArcSIF, freely downloadable. The researchers working on this topic give media interviews and publish on social media. There is no suppressed data. The gaps in our knowledge are not hidden. They are openly discussed in the scientific literature as, "We haven't found the large objects yet, we need better surveys." And here's the pivot that matters. The conspiracy framing isn't needed. The story without it is alarming enough. The real fingerprint, the human fingerprint that doesn't require anyone to be lying, is this. A congressional mandate was passed in 2005 directing NASA to catalog 90% of potentially hazardous near-Earth objects larger than 140 meters. 21 years later, the mission specifically designed to fulfill that mandate is delayed, underfunded, and facing proposed budget cuts of nearly half the agency's science portfolio. Not because anyone decided it wasn't important, because it kept losing budget fights against other priorities across multiple administrations. While the swarm encounter it was most urgently needed to observe kept getting closer. The gap between what the science says needs to happen and what institutional budgets have produced is not a secret. It is the official record, visible in congressional appropriations documents, in NASA budget requests, in Space News articles covering each successive delay. The failure is bureaucratic and political, not conspiratorial. That makes it, in some ways, harder to address. Because there's no single decision maker to confront, no moment of deliberate suppression to expose. Just a long sequence of competing priorities and insufficient follow-through, producing an outcome that looks, from the outside, indistinguishable from negligence. The conspiracy explanation is wrong. The bureaucratic explanation is well documented and not reassuring. The actual physics, the swarm, the blind spot, the 2032 window, the delayed telescope, doesn't need embellishment. It stands on its own. On September 26, 2022, a NASA spacecraft called DART, the Double Asteroid Redirection Test, traveled 160 million kilometers to intercept a small asteroid called Dimorphos, orbiting a larger asteroid called Didymos in a binary system. The spacecraft massed about 570 kilograms. Dimorphos massed approximately 5 billion kilograms. At the moment of impact, DART was traveling at approximately 22,000 kilometers per hour. Before impact, Dimorphos orbited Didymos every 11 hours and 55 minutes. The mission goal was to shorten that orbital period by at least 73 seconds, proving that a kinetic impactor could meaningfully redirect an asteroid. The result? 33 minutes, not 73 seconds. 33 minutes. The mission achieved roughly 26 times its minimum success threshold, validating the kinetic impactor concept far beyond what the models had predicted. ESA's Hera mission, launched in October 2024, is now en route to Dimorphos to characterize the aftermath in detail, measuring exactly how the impact changed the asteroid's orbit and structure, building the database that future planetary defense missions will depend on. The technology works. This is not in doubt. If you find a hazardous asteroid with enough lead time and you have a spacecraft ready, you can deflect it. The physics has been demonstrated. The question for the Taurid swarm is not whether deflection is possible. The question is what enough lead time means, and whether the 2032 and 2036 encounter windows allow for it. DART itself was a mission that took approximately 4 years from formal approval to launch, and it was targeting a known object whose orbit was already well characterized. Before you can launch a deflection mission, you need to know what you're deflecting. You need orbital data precise enough to determine not just that an object might intersect Earth's orbit, but when, where, and what its physical properties are. DART targeted Dimorphos because Dimorphos was already known. A Taurid swarm object first detected in, say, 2031 during the approach to the 2032 encounter would not be a known object with a well-characterized orbit. It would be a newly discovered asteroid with a few nights of observational data. Exactly the situation in which planning and executing a deflection mission within an operationally meaningful timeline is essentially impossible. November 2032 is 6 years and 7 months from today. A mission conceived in response to a 2031 detection needing 2 to 3 years of development and a transit time of several months to a year would arrive too late. The deflection timeline is not flexible in ways that make late detection acceptable. This is why the Boslow paper's language about survey campaigns is not academic hedging. When researchers state that targeted surveys dedicated to quantification of the population, identification of potentially hazardous objects, and detection of imminent impactors during the passage of the swarm should be implemented, the word imminent is doing specific work. An impactor is imminent if its orbital trajectory intersects Earth's in the near future. Detecting it as imminent rather than potential requires a survey conducted while the object is still far enough from Earth that something can be done. For the November 2032 encounter, the geometry is partially favorable. The swarm approaches from the night side. Ground-based optical telescopes can observe the encounter region in the weeks before and during the peak. A well-resourced observational campaign with large aperture telescopes, the kind of effort that the planetary defense community is now explicitly recommending, could potentially identify large swarm members before they become imminent threats. If NEO Surveyor is operational by late 2029 or 2030, it could provide 3 years of infrared survey data on the approach region before the encounter, dramatically improving the odds of early detection. The timeline is tight, not impossible, but tight, and it depends entirely on NEO Surveyor launching on schedule and performing as designed. The 2036 encounter is a different problem entirely, one that doesn't get better with ground-based surveys, no matter how well-resourced they are. That's the subject of the next section. There's a symmetry to Earth's relationship with the Taurid stream that shapes everything about this investigation. Twice a year, Earth's orbit crosses the stream's path, once in October and November, the night side crossing, producing the Halloween fireballs, visible to every telescope on the planet, the subject of dedicated observational campaigns and fireball networks and all-sky camera arrays. Once in June and July, the day side crossing, approaching from the direction of the sun, invisible to optical astronomy, detectable only by radar and radio and thermal infrared instruments that can operate in the solar glare. The 2032 encounter. The exceptional one, the close approach to the swarm center, the one Boslow and colleagues studied for the Cape Town paper, is a November encounter. It approaches from the night side. It can be observed. Ground-based telescopes can look into it. If there are hazardous objects in the swarm's core during the 2032 window, and if surveys are conducted, it is at least possible to find them. The 2036 encounter is a June encounter. June 2036, on the orbital calendar, the Beta Taurid peak, the daytime side, the radiant sitting 10 to 15 degrees from the solar disk, invisible from the ground. Objects moving through the 2036 encounter follow the same geometric approach path as the Tunguska impactor of June 30th, 1908. The same orbital family, the same direction, the same invisibility. Let's be specific about what this means in terms of energy. The Chelyabinsk impactor was 20 meters in diameter. It released approximately half a megaton of energy, the equivalent of 35 Hiroshima bombs, and injured more than 1,500 people, while damaging or destroying more than 7,000 buildings. That was 20 meters. Now scale upward. Kinetic energy scales with mass, and mass scales with the cube of diameter at constant density. A 100-meter object traveling at the same velocity as Chelyabinsk is 5 times larger in each dimension, meaning it has 125 times the mass and 125 times the kinetic energy. At Chelyabinsk's entry velocity, that's approximately 60 megatons. If it reaches the ground or explodes at low altitude, the blast radius covers a major metropolitan area. If it explodes higher, the shockwave footprint covers a region the size of a small country. A June 2036 encounter involving an object of that size coming from the direction of the sun would arrive with no warning from ground-based systems. Not reduced warning, not hours instead of days, zero warning. The first indication would be the fireball. From the Sun-Earth L1 Lagrange point 1.5 million kilometers sunward, the geometry is different. A telescope at L1 can look toward the sun from outside Earth's shadow and see objects crossing the solar disk region against the background of deep space rather than against the solar glare. Amy Mainzer has described this explicitly. NEO surveyors L1 position allows it to detect objects approaching Earth from the direction of the sun, the precise configuration that produces this blind spot for ground-based systems. If NEO Surveyor is operational in June 2036, which requires launching in late 2027, completing its 6-month verification, and maintaining operational status for approximately 8 years, it could provide the early detection that makes a June 2036 swarm encounter observable. Not certain to be hazardous, but observable, known. Boslow's team calculated that Neomir, the ESA equivalent, would have detected the Chelyabinsk object approximately 1 week before impact if it had been operational in 2013. 1 week is not enough time to deflect an object, but it is enough time to evacuate a city, issue population warnings, position emergency resources, and reduce casualties by potentially orders of magnitude. ESA's Neomir mission is targeting launch in the mid-2030s. It will not be operational in time for 2036 under any current planning scenario. The only L1 capable infrared instrument with a realistic chance of being operational for June 2036 is NEO Surveyor. If it launches in late 2027, if its survey verification completes on schedule, and if the fiscal and political environment allows it to operate continuously through the mid-2030s. That is a chain of conditional dependencies involving an instrument program that has experienced approximately 7 major budget or schedule disruptions since 2006. 2032 is the visible problem, 2036 is the invisible one, and they are separated by less than 4 years. We've laid out a substantial body of evidence across this investigation. The Taurid Resonant Swarm is a real predicted structure, confirmed by 3 decades of fireball data, seismic signatures, and orbital analysis. The June encounter of the stream approaches from the direction of the Sun, invisible to ground-based optical astronomy. Tunguska almost certainly came from this direction. The Planetary Defense Telescope designed to close this blind spot has been delayed through repeated budget cycles and may not be operational for the most important upcoming encounter windows. A peer-reviewed paper presented at the 2025 Planetary Defense Conference formally identified November 2032 and June 2036 as elevated risk windows requiring targeted surveys. Now it's time to do something that this kind of investigation requires. Present the competing interpretations of what all of this actually means. Not in the spirit of false balance, but because the evidence genuinely supports multiple readings, and the differences between those readings matter enormously for what humanity should do next. There are 3 interpretations. We'll present them in order from most benign to most concerning, as fairly as the evidence permits. Interpretation 1. The Taurid Resonant Swarm, as it is currently understood by the best available data, is a sparse and relatively small object population. The 2022 surveys, the ZTF observations, and the 3-night CFHT Megacam campaign produced no confirmed hazardous members. The upper bounds they established, while not fully constraining the population at all sizes, are consistent with a swarm that poses no materially elevated risk above the general background near-Earth object population. The elevated fireball rates in swarm years represent meter-class objects. Spectacular and scientifically interesting, but not physically threatening to Earth's surface or to human populations. On this interpretation, the 2032 and 2036 encounters will produce increased fireball activity and excellent scientific opportunities for characterizing the swarm's small body population. They will not produce any object encounters of the kind that require emergency response. The Boslow paper's framing of a coherent component to risk is technically valid but practically irrelevant. The coherent component may exist, but its magnitude is small enough that it doesn't significantly change the actual probability of a damaging event in 2032 or 2036 compared to any other year. Neo-surveyors' delay on this interpretation is a genuine loss for planetary science and a frustrating bureaucratic failure, but not a crisis. The mission, when eventually operational, will characterize the swarm at larger sizes and almost certainly confirm that it does not contain a population of city-killer asteroids significant enough to alter the risk picture. The data that would confirm this interpretation, comprehensive surveys of the 2032 November encounter, finding no new large objects, the June 2036 encounter, passing without detectable hazardous objects once NEO surveyor or NEOMIR is eventually operational. Interpretation 2. The swarm contains a population of Tunguska-class objects, 50 to 100 meter bodies, that the current surveys have been too limited, too brief, and too geometrically constrained to detect. This is not speculation. The 2022 surveys covered a narrow slice of the swarm's volume, lasted 3 nights, and were not optimized for the largest potentially hazardous sizes. The upper bound of fewer than 30,000 objects at 34 to 78 meters is a 95% confidence limit on what was surveyed. It says nothing definitive about what wasn't surveyed. Boslow's coherent risk framing is accurate and meaningful. The standard stochastic impact risk model produces an underestimate for swarm encounter years because it doesn't account for the non-random clustering of hazardous objects in the resonant zone. During 2032 and 2036, Earth's impact risk from objects in this size range is genuinely elevated above the background rate by a factor that cannot be quantified without better survey data. No impact is imminent. No specific tracked object is on a collision course. But the probability of a Tunguska-scale airburst event during a swarm encounter year, given a swarm population consistent with what the physics predicts and the surveys have not ruled out, is meaningfully different from the probability in a non-swarm year. The 2032 encounter demands targeted surveys with the most capable available instruments, and the delay of NEO-Surveyor represents a real and significant gap in humanity's ability to characterize the hazard in the critical window. The data that would confirm this interpretation: surveys during 2032 finding one or more large swarm members on non-hazardous orbits, objects in the 100 to 300 meter range, definitely Taurid resonant members, definitely not Earth intersecting, but existing in the swarm's core, in numbers consistent with a hazardous population. This would validate the coherent risk model without requiring an impact prediction. Interpretation 3. The swarm contains a population of city-killer class objects, 100 meters to several hundred meters, whose existence has been obscured by the combination of the detection blind spot, the narrow and incomplete survey windows, and the systematic bias toward night-side encounters in all historical observations. The Tunguska event was not the statistical outlier it appears to be when modeled against a randomly distributed NEO population. It was a sample drawn from a more hazardous distribution, one concentrated in the resonant swarm, and one that the observational record to date has been structurally unable to characterize. The 2022 survey's upper bound permits a substantial hazardous population in size ranges above what was effectively searched. The model predicts concentration. The physics predicts that objects surviving from the original cometary breakup at sizes relevant to the hazardous range would tend to be trapped in the resonance zone, not randomly dispersed. The fact that no large swarm members have been found does not mean they don't exist. It means the searches have been inadequate. If the June 2036 encounter involves the swarm's densest region passing close to Earth, and the orbital models suggest it may, and NEO-Surveyor is not yet fully operational. The scenario is this: an unknown population of city-killer class objects approaches from the direction of the Sun at entry velocities around 27 kilometers per second, completely invisible to every ground-based instrument on the planet, with no warning available until atmospheric entry. The first indication a populated region receives is a fireball. The first indication of scale is the shockwave. The first indication of consequences is the destruction pattern. This is not a prediction. It is a physical possibility that the current state of planetary defense capability cannot exclude. The data that would distinguish all three interpretations from each other is the same data that Boslow and colleagues called for in their Cape Town paper: comprehensive, targeted surveys of the 2032 and 2036 swarm node crossings, conducted with the most capable available instruments, with specific attention to the 100-meter plus size range that previous surveys have not effectively constrained, and for 2036 specifically, a space-based infrared telescope at L1, operational and conducting active surveys. Strip everything back, remove the interpretations, remove the projections, remove the institutional history and the budget battles and the failed surveys. What does the evidence actually confirm? 7 things. 1. The Taurid Resonant Swarm is a real predicted structure, and its predicted observable signatures, elevated fireball rates, concentrations of larger than average Taurid meteors in specific years, elevated lunar impact seismic activity in 1975, have been confirmed across multiple independent data sets spanning nearly 30 years of observation. The swarm is not a hypothesis waiting for confirmation. Its small body signatures are confirmed. What is unconfirmed is the population in the hazardous size range. 2. The June encounter of the Taurid stream, the Beta Taurid encounter, approaches from the direction of the Sun, placing the radiant only 10 to 15 degrees from the solar disk. No ground-based optical telescope can observe in this direction. This is not a temporary technical limitation. It is a structural consequence of Earth's orbital geometry relative to the stream's approach direction during the June crossing. Chelyabinsk confirmed in 2013 that this blind spot is real, operationally significant, and capable of delivering objects with zero warning. Tunguska in 1908 was almost certainly another demonstration of the same structural blind spot. 3. No comprehensive survey of the Taurid Resonant Swarm at the potentially hazardous size range, objects 100 meters and above, in the resonant zone has ever been successfully completed. The 2019 opportunity, the best geometry since 1975, was lost to the Mauna Kea protests. The 2022 surveys were incomplete in coverage and constrained in depth. The most recent assessment of the swarm's hazardous population remains, uncharacterized at the sizes that matter most. 4. Researchers at the 2025 International Astronautical Academy Planetary Defense Conference, including the researcher most responsible for refuting overblown Taurid threat claims, formally published a paper identifying November 2032 and June 2036 as elevated risk windows requiring dedicated survey campaigns, and stating that the risk from airburst-sized near-Earth objects during these windows may be larger than standard risk models estimate. 5. NEO Surveyor, the infrared space telescope specifically designed and mandated to detect sun-approaching asteroids, positioned at the Sun-Earth L1 Lagrange point, is currently scheduled to launch no earlier than September 2027, with an operational survey phase beginning no earlier than mid-2028. It has been delayed from its original 2026 launch target by a sequence of budget shortfalls and funding redirections spanning multiple administrations. The most recent proposed NASA budget would cut the agency's Science Mission Directorate by 47%. 6. No equivalent space-based infrared survey capability will be operational before the 2032 encounter. ESA's NEOMIR targets the mid-2030s. The November 2032 encounter will be observed, if it is comprehensively observed at all, primarily by ground-based optical telescopes, which can observe the night-side November approach, but cannot observe the day-side June approach geometry. 7. The 2036 encounter is a June encounter. It approaches from the dayside. It is invisible from the ground. If NEO Surveyor is operational in June 2036 and conducting active surveys, it can observe this encounter. If it is not, the encounter is essentially unobservable with current planetary defense infrastructure. That's the confirmed evidence. 7 data points. No speculation required. The question the primary open loop established at the beginning of this investigation was whether the objects coming through this debris field could be detected in time to respond. The answer the evidence produces is this. For the November 2032 encounter, detection is possible if the right instruments are deployed and the surveys are conducted during the approach window. For the June 2036 encounter, detection is only possible from a space-based infrared platform at L1, specifically NEO Surveyor, if it is operational. The gap between possible if and will happen is where this investigation lives. The Taurid Resonant Swarm has been orbiting the inner solar system for somewhere between 10 and 20,000 years. It was there before Tunguska. It will be there in 2032. It will be there in 2036. The debris field doesn't adjust its schedule to match humanity's funding cycles. What this investigation has found is a story with a clear structure. A giant comet died 10 to 20,000 years ago and left its debris in Earth-crossing orbits. A dense cluster within that debris, organized by Jupiter's gravity into a resonant swarm, has been tracked, modeled, and partially confirmed over 30 years of observation. The most dangerous part of the swarm, the region containing the largest undiscovered objects, approaches Earth periodically from the one direction our best telescopes cannot see. The instrument built to close that blind spot has been delayed through multiple administrations, driven by budget dysfunction that has nothing to do with the scientific case for the mission, which has been clear since at least 2019. The next critical encounter is 6 years and 7 months away. The encounter after that, from the day side is less than 10 years away, and the last dedicated search for hazardous objects in the swarm was a 3-night survey in October 2022 that found nothing, which means either there's nothing there or the survey didn't look in the right place at the right depth for long enough. We don't know which of those is true. That's the honest answer. We don't know. What we know is that knowing, actually knowing, with the data to distinguish between Interpretation 1 and Interpretation 3 requires a space-based infrared telescope in orbit and conducting active surveys before November 2032. It requires the kind of dedicated, targeted observation campaign that the Cape Town paper recommended explicitly. Not passive monitoring, not the kind of survey you run when you happen to have telescope time available, but a committed effort to look directly into the swarm at the sizes that matter for long enough to characterize what's there. Signal Watch will be tracking this story as it develops. When NEO surveyors' launch status changes, either a confirmed launch date or another delay, we will report it. When the 2032 swarm encounter approaches and surveys begin, we will cover them in detail. When the data comes in, whatever it shows, we will be here. The researchers whose work this investigation has drawn on, Boslow, Wiegert, Clark, Brown, Mainzer, the broader community working on this problem, are not doomcasters. They are scientists conducting a systematic investigation into a real and unresolved hazard. Their recommendation is not panic. Their recommendation is look carefully before the window closes. 6 years and 7 months. The swarm doesn't wait.